Hey, welcome to computer science lesson here. We are going to be studying how computers store memory and perform basic operations. In order to do that, we're going to begin with learning about number bases. Number bases are kind of tricky at first, but once you get used to them, you realize that they're really just the same thing you've always done. So let's start by talking about what exactly is a number-based system. You may have heard of binary or hexadecimal before, and maybe wondered what they meant. You may have heard that in a computer everything is ones and zeros, which in a way is actually true. Well, what we're talking about there is something called number bases. So let's first talk about what is a number base. So when we have a number based system, each place value has a base. So we use what's called the base 10 system. So that if I write out the number 35923, we call this the ones digit. And this is the tens. And then here's the 100s. I'm not spelling that correctly. And this is the thousandth. And then the 10,000ths. Etc. Well, what these really are powers of 10. This ones digit is actually 10 to the 0 powers because there are 0 tens here. If I have just the number 3 here, this number right at the end, then what we're saying is that there are no tens but 3 ones. This is 2 tens and 3 ones. And then this here is 900 tens plus 2 tens plus 3 ones. Let's take a look at how this would look if we were to expand it. So what does this number look like if we expand it? So we're going to expand 35923, and this is something that you probably studied briefly in middle school and maybe didn't really know why. So what we're starting with is the power of this first number here. It would be probably easier to start on the right, but then our number is kind of backwards. So I'm going to start on the left, but I need to figure out what power of 10 that is. So I start with this, and I say, well, that's 0, 1, 2, 3, and that's 4. So this number here, 35923, is 3 times 10 to the 4th power plus 5 times 10 to the 3rd power plus 9 times 10 to the 2nd power plus 2 times 10 to the 1st power plus 3 times 10 to the 0 power. All right, well, we can actually clean this up a little bit. This 3 times 10 to the 0. Well, it turns out that any number to a 0 power is actually a 1. So this is really just 3 times 1, which is why we call that the ones digit. So I'm just going to erase that. I don't need that. And of course, anything to the first power is just itself, so I'm not going to use that either. Now, believe it or not, this number really is the same as 35923. Let me do some simplification to show why. So I'm just going to call this check. So as far as expanding goes, we've expanded it properly. We've completed that problem. So 10, when you multiply by 10, you just add, when you multiply by a power of 10, you just add how many zeros there are. So 10 to the 4th power is a 1 with 4 zeros. So when I multiply it by 3, I get a 3 followed by 4 zeros. Then a 5 followed by 3 zeros. Then a 9 followed by 2 zeros. And then a 2 followed by 1 zero. And then a 3. So when I add that up, you see I have a 3 times 20 is 23. 23 times 900 is 923. 923 plus, oops, I am missing a 0. 5 times 10 to the 3rd. Okay. Then 5,000 times 923 is 5,923. And then 30,000 times 5,923 is 35,923. All right, let's try another one. This kind of system also works for decimal numbers. So let's try that right quick. Let's do 1524.6. We're going to expand that. What would that look like expanded? Well, we're going to start again with this far left number. This is the 0 power, the 1 power of 10, the 2 power of 10, and the 3 power of 10. So what does that make this power? Well, that's the negative 1 power. So this is 1 times 10 to the third plus 5 times 10 to the second plus 2 times 10 to the first plus 4 times 10 to the 0 plus 6 times 10 to the negative 1. 10 to the negative 1 means 1 divided by 10. And anytime you multiply by 10 to a negative power, you just move the decimal 1 to the left. So 6 times 10 to the negative 1 is actually equal to 0.6. So this value here is 0.6, and that's 4, and that's 20, and that's 500, and that's 1,000. So it clearly works. Okay? All right, I'm going to give you a couple to try. Okay, so try these two. I want you to expand them. You don't need to check or anything like that. Just write it out as a powers of 10. Okay, let's see how you did. Hopefully you paused the video. You should pause the video and make sure you do this. But now that you've done it, hopefully, let's go over it. This is 2 times 10 to the second plus 4 times 10 to the first. Plus, remember, we starting at the decimal. The number just left of the decimal is a power of 0. Always remember that's 0, that's 1, that's 2. Okay, so plus 2 times 10 to the 0 plus 9 times 10 to the negative 1 plus 8 times 10 to the negative 2 plus 2 times 10 to the negative 3. All right, let's try this one. This is, when it's just an integer number, we can just count the number of digits. There's 1, 2, 3, 4, 5, 6, 7. But since that first place is 0, that means that I'm going to start with 6. So this is 1 times 10 to the 6th plus 8 times 10 to the 5th plus 7 times 10 to the 4th plus 0 times 10 to the 3rd plus 0 times 10 to the 2nd plus 3 times 10 to the 1st plus 0 times 10 to the 0. All right, and you probably could have left off these 0 times things, and that would have been fine, or left off powers of 1. We know we don't need that, or powers of 1 are just 10, and 10 to the 0 is just 1. All right, so what I want to tell you is that this principle that I can expand things out and they end up being the same number is not unique to base 10. We are in a base 10 system because each place value is considered a base of 10. But we don't have to use base 10. So let's look at an example of a different base. So now I want us to expand this number. We're going to expand 2314 that is in base 5. So when I write the little subscript here, this thing here is saying I'm in base 5. So in base 5, the numbers that we have available to us are 0, or I should say the digits we have available to us are 0, 1, 2, 3, and 4. There is no 5 in base 5, just says there's no 10 in base 10. And that sounds weird. You're like, how could there not be a 10 in base 10? I see 10 all the time. Well, what you see is a 1 and a 0. But we don't have a single digit that is worth a value of 10. The highest digit we have is 9. Now, how many digits do we have in our base 10 system? Well, we have 10. You can look at your keyboard and see that there are 10 numbers on it. If you go from 1 on the left all the way up to 9, and then they put the 0 on the right. In a base 5 system, you have 5 digits as well: 0, 1, 2, 3, and 4. Okay, but you're gonna begin to understand that as we go forward. But for now, just understand that this principle is exactly the same. 2314 base 5 is 2 times 5 to what power? Well, this is remember this is the 5 to the power of 0. This is the ones digit no matter what. And this is actually the 5's digit. This is 5 to the first, and this is the 25's digits, and this is the 125th digit. But you don't need to know all that. Just know that you start with this digit just to the left of the decimal point is power 0, then power 1, 2, 3, etc. So this is 2 times 5 to the third plus 3 times 5 to the second plus 1 times 5 to the first plus 4 times 5 to the 0. So this is our answer. We've expanded it. But I do want to go through and check this one because I want you to understand that this number really is a value. Well, let's figure out what it is. But let's figure out what it is in base 10. So the way we're going to do this is we're going to just simply do our math as we normally would. 5 to the third power is 125. So this is 2 times 125. 5 to the second power is 25. So this is 3 times 25. 5 to the first, of course, is just 5. And anything to the 0 power is 1. So it's just 4 times 1. So 125 times 2 is 250. Then that's 75. That's 5. And that's 4. So this ends up becoming, let's see here, 250 plus 7. I need to do some scratch work, right? 250 plus 75, 5, and then 1, 2. So that's 325. But now I got to add 5 to that, so I get 330. Then I got to add 4 to that, so I get 334. So I have 334, and that's in base 10. And if we don't put the base, it's assumed to be base 10. So that's how that works. Now, let's just take a couple of moments to appreciate this. Do note that the number is less digits. We only used 3 digits when we were in base 10. Totally normal. That makes perfect sense to me because in base 5, since we only have the digits up to 4, it would make sense that we would need more digits to express the same quantity. The other thing I want to point out is that the math was kind of tricky here when I tried to convert it back to base 10. I had to add some numbers. It wasn't nearly as easy as when we were checking our base 10 expansion. But if I were to keep this in base 5, it would be totally normal. Because in base 5, 5 to the third is simply 1, 0, 0, 0. It's just a 1 with 3 zeros. This is just a 1 with 2 zeros. And this is just a 1 with 1 0. And this is just a 1. So in base 5, it would just be 2, 3, 1, 4 when you do the math backwards. But it's this step here when I started putting 5 to the third in terms of base 10. Because 5 to the third in base 5 is 1 with 3 zeros. Because that's how the number bases work. But 5 in base 10 is 125, and that's where the math got more complicated. All right, so what I want you to do now is I want you to try and expand and then figure out by converting to base 10 what this number would be in our base 10 system. So I've got the number 3132 base 4. So pause. I'll use a different color for the base because it's kind of hard to see. Base 4. So pause the video. I want you to first expand it and then go ahead and finish by converting it to base 10 to kind of solve the mystery of what this number would be. Okay, let's see how you did. You should have said, since there are 4 digits, 0, 1, 2, 3, 3 is the highest power on 4. So 3 times 4 to the third, plus 1 times 4 to the second, plus 3 times 4 to the first, plus 3 times 4 to the, oh, I'm sorry, that should be a 2, right? 2 times 4 to the 0. Okay, 4 to the third is 64, And so in 4 to the third is 64 in base 10, right? So I got to do 3 times 64. Let's see, 12. 18 plus 1 is 19, so that's 192. 4 squared is 16, so plus 16. 3 times 4 is 12. And then 4 to the 0 is a 1, so 2 times 1 is 2. And again, the math is getting a little ugly here, isn't it? But that's okay. So 8, and then carry the 1. So that's 208 for the first two. Now I got to add 12 to that. Oh, carry the 1, and 2. So that's 220, and then I need to just add 2. So that's 2, 2, 2 in base 10. All right. Now I think we've talked about it, we've hyped it up. Let's talk a little bit about binary. Okay. So let's start with the number 1011. Binary, base 2. Binary. So what does that mean? Binary. Well, the prefix bi just means that it's a base 2. Okay. Now each one of these places here we know are called digits. So a special word for a digit in binary, we call it a binary digit. Make sense? So a binary digit is either a 0 or a 1, because you can't have a 2 in binary, right? Now, this word here is kind of a mouthful, binary digit. So what we do is we just kind of sandwich those two words together, right? Actually, we even we just do that. So we just kind of sandwich those words together, and we get what's called a bit. I bet you've heard of that before, haven't you? You've probably heard of a bit. A bit just means binary digit. That's all it means. So, earlier we had a base 4 digit, and I think we had a base 5 digit. Now we have a base 2 digit called a bit. So let's see if you can't figure this out. If you don't know your powers of 2, just figure it out, write it out. But I want you to convert the binary number 1011 into base 10. All right, let's see what this would be in base 10. This is a 1 times 2 to the, there's 4 digits here, so that's to the third, plus 0 times 2 to the second, plus 1 times 2 to the first, plus 1 times 2 to the 0. 2 to the third, 2, 4, then 8. So that's 8. 2 to the second is 4, but times 0 is just 0. And 2 to the first is 2, times 1 is 2, and then 2 to the 0 is 1, so just plus a 1. So what we end up with is 11. 1011 in base 2 is equivalent to 11. It looks like another binary number, but it's not. Okay, now maybe you've heard of hexadecimal, right? Have you heard of hexadecimal numbers before? Hexadecimal are a number system in what's called base 16. I'm not really sure where the hex comes from. Well, I guess because decimal means base 10, by the way, if you didn't know that. Decimal, deci for 10, so hexadecimal means 6 plus 10, I guess, so that's where I get that. Let's take a look at it. So I've got a number here, 1F, 3A, and that's in base 16. So what in the world are these things, F and A? Well, it's really not that complicated. You see, in base 16, we have more than 10 digits. We have 16 digits. They start at 0, just like we're used to, and count up. 5, 6, 7, 8, 9. But then what's the next number? Now, you can't say 10, because 10 would be actually 16 in base 16, because it'd be a 1 and then a 0. So we need a single digit representing 10. Well, I don't know. You could maybe try X for Roman numerals, but then what we do for 11? It's got to be a single digit. I don't know. Maybe a squiggly line or something like that. They could have invented anything, right? They could have made, new different digits or something like that. maybe like a number like that. Maybe, I don't know. But they decided not to do that. The people making this said, you know what, we're going to keep it simple. We will just use letters. So we'll start with A. So A is the value 10. And then we get B for 11, C for 12, D for 13, E for 14, F for 15, but there is no 16 in base 16. So that's why F is the highest one. So let's expand this one. We have 1 times 16 to the third plus F times 16 to the second plus 3 times 16 to the first plus A times 16 to the 0. Well, 16 to the third, 16 squared is 256. So let's, this is getting a little bit more mathy than I would like, but that's okay. We can do it. 33, and then 12 plus 3 is 15. And then I just put 6 and a 5 and a 2, I think, right? So 6, 9, 1, 0. So 4,096. So this is 4,096. And then we said that 16 squared, that's 256. I know that one. So this is, F is 15. So this is 15 times 256. And then 3 times 16 is 48. And A is 10. And 10 times 1 is just 10. So now I got to do 256 times 15. So that's a 30. 25 plus 3 is 28. And then that makes that a 12. Then 6, 5, and 2. So 0, 1, 4, 8. So 3840. So I have 4,096 plus 3,840 plus 48 plus 10. Well, let's add these two together right quick. That's 6, 1, 3, 9. So 7936. Hopefully I'm not making any little arithmetic errors. That's not really the point anyway. I'm just trying to get you the idea of these number systems. So 14, 8, 7984. And now I just got to add 10 to that. That's easy. 7994 in base 10. That's what this number becomes in base 10. All right. So that is converting numbers from one base to base 10. Obviously, when you do the conversion and you're already in base 10, it just takes you right back to the number. So the process, remember, to convert a number from one base to base 10 is to simply expand the number out and then do the basic arithmetic, and it will convert it to base 10. You might not be sure why we would have numbers in different bases yet. That's okay. But we're going to stop with just this lesson, and I'm going to ask you to do a few practice problems where you convert some things into base 10. In the next lessons, we'll be looking at how to convert from base 10 to another base, and we'll begin to study things like the binary and the hexadecimal system, and also probably base 8 in a little bit more detail. We'll do that, and we'll start to then discuss why. Why would we want to use such a number-based system? Okay, so we're going to continue with this number-based unit for the foreseeable future until we get this down, and then we'll start applying it in our programs. And so I look forward to spending time with you on it.